So here we got another example of a super cool topic of optimization. Now here it says a rectangle has a length of x and its perimeter is 20 meters. What is the maximum area of such a rectangle? Well, so in a sense, we got to first start writing out the information we have. We know that perimeter would be equal to 20, and as this is a rectangle, in case you don't remember, well, a rectangle, its perimeter be equal to 20, we know that. Equal to 20, and also the perimeter of a rectangle would be equal to twice the length, which I'm going to call this x and y. I'm going to call perimeter would be equal to twice x plus twice the width, which is y, I'm going to call it. So in a sense, if we mix up this information, we'll get that 20, which is the perimeter, will be equal to 2 times x plus 2 times y. So this would be, I'm just going to write a different color just to make this as clear as possible. This is our perimeter. There it is. Now, we also have this other piece of information about the area, which I'm going to call area. The area, it's equal the length times the width. Now, this presents a problem because we have here two variables. And so far, we have only seen kind of problems. If I write this properly, be a of x times y. So we got to figure out a way to reduce one variable out of this expression, because so far we have only seen functions where we have only one variable and we have two. So pretty much we got to find a way to reduce one of these variables. So well, that's why we got the perimeter in a sense. Look, if I solve here for one of the two variables, I'm going to solve for x. 20 minus 2 times y will be equal to 2 times x. Now I divide both sides by 2. We get this 20 minus 2 times y equal to x, but this will be all over. Be nicer this way. All over 2. So will be x at the end. In this case will be equal to, I'm going to write it more on the left just to save space. X will be equal to, well, you divide 20 over 2, will make it 10. And that will be minus, well, 2 times y over 2, that will make a y. And that's the first thing we got, you know. This would be equal to, I'm going to use green color just to frame it. This is one piece of information, very helpful, that we can use. You know, if you substitute this information, if you substitute this equivalence for x, then you will find yourself in a case where you will have only one variable. Just look at it. We found that x was equal to the what is 10 minus y, 10 minus y, and then will be times the y. But now here the key is that once we substitute, we took away the x. We took away the x once we substitute this, and now everything of the area is expressed in terms of one variable, which is a y. Now that will change this. This will no longer be a function of x and y, but only a function in terms of y. There it is, in terms of y. So in this case, we got to pretty much, in order to maximize or to find the maximum possible area of this rectangle, well, it'd be wiser just to multiply everything out, just to make this easier to take a derivative of. There it is. Now, if you are looking for the maximum or the maximum possible value for a function, well, in a sense, it's a key just to get this topic of optimization. So we're going to pretty much, take the derivative, the same steps. Would be 10 minus 2 times y. That we equalize to 0. Solve for y. So 2 times y would be equal to 10. and y would be equal to 5. So this value of y, it's our candidate, it's our critical point now. It would be, necessary as well to test whether if this is a maximum or a minimum. Now, of course, this has to be a maximum because otherwise it wouldn't make much sense, this kind of problems. Still, I'm going to test it to prove it so you can see it. So, well, x will be equal to 5. Pick a value 1 after and 1 before. So, well, I'm going to pick here a prime of 0 just because I think it's simpler, although it might not make much sense because we are talking about an area and a perimeter, but I'm still going to use it. It's just out of simplicity. So a prime of 0, that will make a 10. So very okay, 10 minus 2 times 0. Of course, we can cancel out the 2 times 0, and we get at the end with the 10. Now, this is telling us that it's ascending. Function is ascending up to the moment when it reaches the x equal to 5, and then we have to figure out. So I'm going to use, let's say, a prime of 10. So this will be equal to 10 minus 2 times 10. So this will make at the end a negative 190. Now this negative sign is telling us that the function after the x equal to 5, it's descending. Descending. So with all this information now we know that the function, if it's ascending and descending, then this is a maximum. Then this is a maximum. Now this piece of proving whether if it's a maximum or not, well, this seems a bit like protocol, but we still have to do it. It's a maxima. And well, the last thing is, what is the maximum area? What is the maximum possible area for this rectangle? Well, in a sense, we are requested to substitute this other color to find the maximum possible area, or the maximum area. So you have to evaluate at a of x, a of y. I'm sorry. In this case, will be a of y. So well, it's it's pretty much just substituting. So it will be a of 5, and this will be equal to, I'm going to pick this expression to evaluate. So it will be 10 times 5 minus the 5 squared. So this a of 5 would be here, of course, would be here 50 minus 5 squared will be 25. And then at the end, we got this 25. Now, this is 25 would be the maximum possible area. I'm going to write it with the proper units, maximum 25 meters squared. Just going to write it with the proper color. This would be the maximum area, and with this we are done.